Okay, so what we're going to look at in this unit, this is one of the units that we had to put in there kind of to justify it as a college math class. Looking at relationships between different amounts, different quantities. And actually looking at relationships between two variables. When we have two values or two numbers that are linked together, there are a lot of ways that we could display those. We've looked at a little bit at displaying single numbers, like if we have x equals 4. Now when we talked about negatives and stuff like that, we use number lines quite a bit. And there are a couple of different ways we could represent the number 4. We used, for the negatives, for the integers, we used the vectors or the arrows. A shorter way of doing that, if you have a lot of numbers that you want to represent on a single number line, is to just put a dot at 4, and that represents the value of 4. If we have two numbers that we want to represent at the same time because they have some sort of a link to each other, possibly like height and weight or time and a certain level that you're measuring or whatever. If we want to display those graphically, a single number line doesn't work so well. A man by the name of René Descartes came up with a method using a number line to represent both of those variables at the same time. And what he did was he took a number line, pretend those are evenly spaced, to represent the first value, and then to represent the second value, he created a second number line, but this one, instead of going horizontally like we're used to, he made it vertically. And it went through the 0 of the first number line, and of course the 0 of the second number line was in the same spot. And it was numbered positive going up and negative going down. So the 0 of both number lines is in the same spot, and that spot was known as the origin because everything starts at 0 and both of them started at that spot, so that was the origin of both number lines, or the beginning of both number lines. To represent a pair of numbers, let's say we have the pair 4 and 7 that we want to represent together as a pair. We would find 4 on one number line, right here is the 4, and 7 on the other, right here. And to show that those are linked together, we projected them out and we put a dot right here out in space. And the shadow of that dot on each number line was its value. So the shadow going down, as we saw, was on the 4. The shadow going over was on the 7. So that dot represents both of those values. Now, a couple of things we need to define. We need to figure out, how do we know which number goes on which axis? Well, we usually define this axis here is often what's called the x-axis, or the x number line. Sometimes also called the independent axis, which we'll explain what that word independent means in just a second. And the vertical one here is called the y-axis, or sometimes called the dependent axis. And when we were setting up our numbers, here we listed 4 and 7 together, the first number is always that independent variable, or the x-axis. The second number is the dependent, or the y-axis. And that makes up what we call an ordered pair. Obviously, it's a pair because it's two numbers, and ordered because they have a specific order that they have to go in. So I said that we would explain this value, this word here, independent. When we talk about statistics and most relationship graphs that we're looking at, the two variables have some sort of relationship. And in many cases, it's kind of like a cause or effect relationship. One variable, bless you, one variable causes a change in the other, or the change in one of the variables is being measured as how it's affected by the change in the first. So the first one, the variable that's the cause, is generally listed as the independent variable. It's very, very common to graph things over time. Time is almost always the independent variable. For example, if you want to look at someone's blood sugar level over time, well, time would go along that x-axis, and the blood sugar level would be up and down on the y-axis. Now, in most practical graphs, what we use is not the whole graph that we have charted here. Most practical graphs, the values stay positive. So all we really use is this top corner of the graph where everything's positive, like that. It's what we call the first quadrant. Quadrant 1 is the way it usually gets labeled, but the first quadrant is fine. And of course, then this would be the second quadrant over here. Why is that called the second quadrant? For a couple of reasons. In math, we tend to go counterclockwise around things. The main reason for that dates back centuries to navigational techniques. When you're looking at directional navigation, if you look at a compass, this is the east direction with 0 degrees, and your navigational directions went around counterclockwise. And everything seems to have kind of adapted that same mode, and everything kind of mimics that as we go through more of the upper level math. Also, it's called the second quadrant because more often than not, that is the second one that's going to be used when we're graphing stuff, if we go back in the reverse direction. So then the third and the fourth quadrant if we continue going around counterclockwise. You don't really need to know second, third, and fourth quadrant. For us, you hear the term first quadrant, you just need to know that that means where both variables are positive, or this section of the graph up here. So about the first thing we need to do is we need to be able to look at the graph and identify points. Let's see if I can do a decent enough job of drawing my graph here. So let's say I put in a point here. Right there. What would the coordinate of that point, or the ordered pair of that point, be? 8 and 3. Perfect. The 8 goes first because it's on this horizontal or independent axis. And then 3 is the vertical axis. How about this point right here? Perfect. 1 and -6. Again, it's the horizontal axis first, which is 1. And then -6 down here is the vertical axis. How about this one? Perfect. -6 and 5. We trace it down to the horizontal axis is -6, and the vertical axis is at 5. Okay, so we don't need to mess around with much more of that. The big thing to be careful of is to know what each of the points are. I often will go back to 0 to the origin and count, because a lot of times when you see these labeled, they might be labeled like this. Because on graph paper, often it's a grid paper where there's lines going here, so they put the numbers in the spacing, which is okay here because there's the origin. You know that this is where the 1 is and that's where the 2 is and so on. But when you get up here, here's the 8. Which one of these lines represents the 8? So just be careful to make sure you figure out where the numbers actually go, what it's actually being labeled as. Okay, so what are these graphs for? We're going to talk about data graphs either later today or early in the class next week. But for right now, we want to talk about graphing generic equations, generic algebraic two-variable graphs. We might have something like y equals 3x minus 2. If we look at that, these equations are a way of expressing several solutions at a single time. We've seen equations like this of 7 equals 3x minus 2. And we were able to solve that equation by doing what? Adding 2 to get 9 equals 3x. And then what do we do? Divide by 3. Perfect. to give us that 3 equals x, or x equals 3. Well, in this one here, we don't have the 7, we have the y. So what this is saying is instead of having a single value of 7, we want to evaluate all of the values that could go there at the same time. Well, we do know that when y is 7, x has to be 3, but there's an infinite number of solutions here. No matter what number we pick for x or y, there is a value for the other one that will make that equation true. So there's no way we're going to be able to list those all out. So what we do is we just start listing out some of those values. So we're going to use a table, and I'm actually going to rewrite this down here. So y equals 3x, or 3 times x minus 2. And we make a table. And for our table, we're just going to pick values of x. Now, I'm going to pick some fairly easy numbers, but I'm not just going to do like 0, 1, 2, 3. I'm going to do like a negative 3, negative 1, 0, 1, and 3. The reason I chose those numbers is we're eventually going to graph these on a graph. And I want some values that not only just positive values here, but I want some values over here so I can get a better picture of how this looks on our graph. So now that I've picked some values for x, and I don't have to pick them all at once, I can just pick a couple values and go from there and then pick more later. And I'll show you that in just a little bit. But now that I've picked some values, I have to figure out what y is. Well, y equals 3x minus 2. So I can use that to figure out what the value of y is. So if x is negative 3, y becomes 3 times negative 3 minus 2. Well, what's 3 times negative 3? Negative 9. Minus 2 is negative 11. So what this is saying is when x is negative 3, y is negative 11. So that's actually an ordered pair of negative 3, negative 11. So on my graph over here, 1, 2, 3, there's negative 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative 11 is down there. So that gives me a point somewhere in there. Next, if x is negative 1, then y is 3 times negative 1 minus 2. What's 3 times negative 1? Negative 3 minus 2, negative 5. So when x is negative 1, y is negative 5. So we get negative 1, negative 5. Like that. X is 0. Y is 3 times 0 minus 2. Well, of course, 3 times 0 is 0. Minus 2 is negative 2. So when x is 0, y is negative 2, giving us the ordered pair 0, negative 2. So x is 0 right there. We don't move side to side at all. We just go down to the negative 2, like that. And then we keep going. If x is 1, y is going to be 3 times 1 minus 2. 3 times 1 is 3 minus 2 is 1. So if x is 1, y is 1. So over here, 1 and 1, there's a point. And then finally, if x is 3, y is going to be 3 times 3 minus 2. 3 times 3 is 9 minus 2 is 7. So x is 3 when y is 7. So 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. Somewhere in there. And we notice it forms a nice straight line if we draw one through those points. What is that line telling us? Well, that line is the solution, all of the solutions to this equation right here. If I pick any point on that line, let's say I pick a point right here. If I trace it to the x-axis, I can get an x value. In this case, it would be 2. If I trace it to the y-axis, I get a y value. That would be 4. What that's saying is when x is 2, y has to be 4. If I put that in here, it would make this equation true. Or if I picked a value for one or the other. Let's say I wanted to pick the value of 5 for y. I could trace that over to the line and then trace it down to x, and I get that x would have to be 2 1/3. When x is 2 1/3, y has to be 5. Not all of our graphs form a nice, pretty little straight line like that. We could have something like this. But we're going to do the same thing. Now, I mentioned that we don't have to pick all of our points right away to begin with. I'm just going to pick a few values for x, and we're going to put them on the graph and see what it looks like, and then we're going to go from there. So I'm going to pick x equals like -2, 0, and +2. And we'll see what we get from there. So y equals x squared plus 2x minus 15. So I'm going to put in -2 where the x is. I'm going to erase these values because I'm going to need some order here. So if x is -2, y is -2 squared plus 2 times -2 minus 15. What is -2 squared? It's 4, right? Any number squared is positive, so -2 squared is a positive 4. 2 times a -2, a -4, and then -15. So we have 4 plus -4, which is 0, minus 15 is a -15. So we get that when x is -2, y is a -15. So somewhere right there is where that point would be. Now we had picked 0. If x is 0, what's y going to be? Well, it would be 0 squared plus 2 times 0 minus 15. Well, what's 0 squared? 0. What's 2 times 0? 0. So if you got 0 plus 0 minus 15, ends up being -15 again. So that gives us a point right there at 0, -15. If this is going to be a straight line, it's going to be flat, isn't it? Well, we had a point of 2. Let's try 2. If x is 2, then y will be 2 squared plus 2 times 2 minus 15. Well, 2 squared is 4. 2 times 2 is 4 minus 15. Well, 4 plus 4 is 8 minus 15 is -7. So when x is 2, y is -7. So here's x is 2, -7's down here, right there. First of all, these 3 points tell us that this is very clearly not going to be a straight line. We need more information, however, to figure out what shape it's going to be. I need to know, well, it'd be nice to get some points up here that would become positive, so I need to go a little bit further out this way to figure out some points. But I really need to go back here as well and figure out some points. So once I've put some points on the graph, I use that to figure out what values for x I want to keep using to figure out the rest of the graph. So it looks like I might choose like x is -4 or something over here. If I were to keep going, let's figure out what's going on when x is -4. So if x is -4, y is -4 squared plus 2 times -4 minus 15. Well, what is -4 squared? Positive 16. 2 times -4, -8, and minus 15. Well, 16 plus a -8 is 8, minus 15 is -7. So at -4, y is -7. Well, that just mirrors this point here, like that. I'd kind of like to know what's going on in between these two here. That would be at x equals -1, so let's try that. As you can see at this point, there are no right numbers that you can choose for x to put in. You just have to keep picking numbers and fill it in until you can see what shape the graph is. There are some standard shapes the graphs might take. There's two of them that we're going to use in here mostly. One is the straight line like we saw in the first example, and the second is what this one is going to be. But there are a lot of other shapes they can take on. We're going to practice some of them, but when I test you in a couple weeks, it will just be the line, and then this one's going to be called a parabola, which we'll go over in a second. But anyway, if x is negative 1, y is going to be negative 1 squared plus 2 times negative 1 minus 15. What's negative 1 squared? 1. 2 times negative 1 is negative 2 minus 15. Well, 1 plus negative 2 is negative 1. Minus 15 is a negative 16. So when x is negative 1, y is negative 16. So that means here at negative 1, it actually goes down one more somewhere in here. Now at this point, you might get the picture that it's starting to do a shape like this. Some of you might want to pick another point or two out here and see what happens. That's fine. This shape is what we call a parabola. It's a pretty standard shape, tends to occur whenever you see that x squared in a problem. Again, it's one of the two shapes that's pretty important to us that we're going to use a lot. What I want to do now is I want to have you guys practice this a little bit. So I've got a worksheet that I'm going to pass out. You can work in groups or whatever you want to do. And what I want you to do is take variables or values, put them in for x in a table, and figure out what the value for y is, like I did here, and plot those points. I gave you, for each of them, I gave you a table where I picked out 4 or 5 values for x for you to try. That doesn't mean that those are going to be enough to graph it. It's just a place to start at. So I'm going to pause this, and I'll pass. So looking at the graphing worksheet, what's the equation on the first one? Y equals 3x minus 3?
2.
Minus 2, okay. So that should look something like this. Second one?
Y equals 6 minus x.
6 minus x. Probably something like that. Third one.
X squared plus 2x.
Something like this. Third one? Or fourth one?
X plus 6.
Something like that. You'll notice on this one, by the way, all of them have arrows on both ends, except for this one has an arrow here, but not here. This one can't keep going in this direction. Because if x were smaller than negative 6, let's say x were negative 7. What's negative 7 plus 6? Negative 1. If we try to take the square root of negative 1, our calculator tells us error. We cannot take the square root of a negative number. How about number 5? 3 plus 3x. So that one should look something like this. 6 2 to the power of x. Looks something like that. Actually, this should be at 1 here, so I got a little high. Number 7. X cubed minus 1. So, something like that. Number 8.
8 divided by x.
Okay, this one's kind of a weird one. I think I gave you numbers like negative 8, negative 4, negative 2, negative 1, something like that.
Negative 1, 1, 2, 8.
Okay. So like if we put in like negative 8, we would have a negative 1 here. Put in negative 4, we'd have a negative 2. A negative 2, we'd have a negative 4. Negative 1, we'd have a negative 8. You get a curve that looks something like this. But what if we put in x equals 0? Well, 8 divided by 0 would once again give us an error on our calculator. X can never equal 0. But if we skip over to positive 1, well, then it would be 8. 2 would be 4. 4 would be 2. We get another curve over here that looks like this. I would never do that to you on a test, by the way. Number 9. 4x squared minus 8. Okay. Yeah, it's going to look something like this. Pretty narrow. And number 10. Something like that. Now, obviously, I can graph these pretty quick, which means there must be some sort of a shortcut. Not that I just have them all memorized, because I don't. But, two things we see. There are two graphs that popped up more than once. Straight line, obviously, is a big one. And then this one here, the parabola. And those are really the two that we are most concerned with. Ones like this, we don't care so much about. This one here is actually useful, but we're not going to get quite that far into it. Same with this one. This is actually a very useful one called an exponential curve, but we just don't have the time to get into it really. But let's look at the ones that form straight lines. We had 1 and 2. It's like 5 and 10 form straight lines. If you look at those 4 and compare them to the other equations, the other graphs and the equations, what's different about those equations? Okay, perfect. That's the first one, is there's no power on the x, or on the y for that matter, actually. And powers, I mean also roots. Like in number 4, I think we had the square root. That's a power of 1/2. So that's one thing that those lines don't have, is they don't have a power on any of the variables. Anything else? Let's look at number 6. What's going on there? Yeah, 2 to the power of x. And that one, the variable is the power. So if one of the variables is a power itself, then there won't be a straight line. And then the last one, I believe it's number 8, I think. Dividing by x, dividing by a variable. The 3 things we've just listed out here are what I call the 3 don'ts of linear equations. If you see an equation and it has one of those 3 things, a power on one of the variables, and as we said, that includes a square root, a variable in the power, or dividing by one of the variables, then we know that that is not going to be a linear equation. So with that, we can look at an equation and very quickly tell whether it's going to form a straight line. Looking at that one, is it going to be a straight line? You're tempted to say no because of the squared, but it's not on the x. 4 squared is just 16. So that will be a straight line. How about that one? No, because there's an x squared there, that's not going to be a straight line. This one? It's good, yeah. It's not how we're used to seeing it because we're used to seeing y equals, but that will be a straight line. This one. We see that square root and it scares us, but does it affect it? No. Square root of 9 is just positive or negative 3, so that is a straight line there. How about that one? Not a straight line because we're dividing by x. We're used to seeing it like this on the worksheet where it's 5 over x, but just 5 divided by x is the same thing. We're dividing by a variable. It will not make a straight line. Okay, so enough of that. Let's actually look then at how we can use shortcuts. Once we know it's going to be a line, how can we graph it quickly? You guys have a great week. Thank you. Let's look at the simplest linear equation I can think of, and that is simply y equals x. If we just pick some quick points for x and put them out here, like if x is negative 3, well then y has to be negative 3, right? If y equals x. If x is 0, y would be 0. If x is positive 3, y would be positive 3. It forms a line across our graph, corner to corner. Get 45 degrees across our graph. Pretend I drew that straight. So that's the simplest linear equation I can think of. Well, what are some things we can do to complicate it? Well, just like when we were solving equations earlier and we were looking at building equations, we can add something to it. We might have y equals x plus 2. Well, what's that going to do? Well, now if x is 0, what's 0 plus 2? 2. So if x is 0, y is 2. If x were 2, y would be 2 plus 2 is 4. Up here. If x were negative 1, well, negative 1 plus 2 is positive 1. It would look like this. And what we get is a line that goes across the graph at the same angle, but it's just moved up 2 spots. So that adding 2 appears to just move it up 2 spots. Let's test that out. What if it were x minus 3? Well, now if x were 0, y is 0 minus 3 is negative 3. If x were 2, what's 2 minus 3? Negative 1. And we can see if we kept plotting points that it does. It gives us a line, goes across the graph at the same angle, it's just moved down 3 spots. Well, some other things we could do might be this. Y equals 2 times x. Well, now if x is 0, y is still 0. So it's back to going through our origin, or the center of our graph. But now if x is 2, y would be, what's 2 times 2? 4. Let's say if x were negative 1, what's 2 times negative 1? Negative 2. So what this does now, multiplying x by a number, we're back to going through the center, but it's made the line steeper. Well, with that in mind, what would happen if we did this, x divided by 2? Now, in algebra, what we tend to do is instead of dividing, we tend to do this. We tend to multiply by 1/2. So instead of saying x divided by 2, most of the time we'd say y equals 1/2 times x, like that. What do you think that's going to do? Multiplying by 2 made it steeper. Dividing by 2 or multiplying by 1/2 is probably going to make it shallower. If x is 0, y is still 0. So let's say x is 4. What's 1/2 of 4? 2. So you can see it does make it shallower. Makes it less steep of a line. But so far, all of the lines we've put on here go up like that as we move from left to right. Different angles, we've moved them up and down by adding or subtracting. We've made the angle different by multiplying or dividing, but we haven't made them go down at all. How do you think we would do that? A negative. Very good. We might do y equals negative 3 times x. Well, now if x is a negative 1, y is a positive 3, because negative 3 times negative 1 is a positive 3. If x is 0, y is still 0. If x is 2, negative 3 times 2 is a negative 6. We get a line that goes down. So what we have is really only two things that we can do to change a linear equation. We could move it up and down, or we can change the angle that the line goes across the graph. So if I have y equals 2x plus 3, we said the center of the graph here was our origin, because that's the starting point. And yes, that's the starting point. Not only is it the starting point of the graph itself, but it's the starting point of the graph of every line or other shape that we do. So if we start there, the positive 3 tells us that we're going to move up 3. And that we're actually going to start up there at positive 3 instead of at 0. The 2 multiplying the x tells us that this line is a little bit steeper, like this. So the question is, how do we get it exactly the right steepness? How do we use that? Well, this number here that multiplies the x is what we call the slope. Slope is defined as rise over run. It's a ratio. Slope is always a fraction. And you might be looking at it and say, well, that was 2 times x. That's not a fraction. Yeah, it is. 2 can be written as a fraction as 2 over 1. The 2 is the rise. So from this point, once we figured out that 3 here was our starting point, from that point we use the slope. We rise 2, we go up 2, and we run 1. So over 1 to right there. Let's take a look. So I have an equation, y equals 3x minus 1. Where am I going to start this equation? Yeah, from the center I go down 1, negative 1. That is my starting point right there, negative 1. My slope is 3, but I make that a fraction by making it 3 over 1. So from this starting point here, I go up 3 and over 1. I rose 1, 2, 3, and I ran 1. That's the second point of my line. My graph, my line goes through those 2 points, like that. So for this one, where am I going to start? Positive 3. So from the center I go up 1, 2, 3. That's my starting point. From there, rise 2, run 3. So there's my second point. My line goes through those 2 points. Where's this one start? Positive 2, because we added 2. Now you'll notice that's a negative 1/2. Now it doesn't matter whether I write it as a negative 1 over 2 or as a negative 1/2 or even 1 over negative 2. What it means is this line goes down as we move from left to right. And the easiest way to interpret it, no matter how it's written, is from this point we go down 1. Our rise is now negative, so we go down 1 and then over 2. So there's our second point right there. Pretend that line is straight. So on this one, where would we start? Negative 2, right? There's our first point, and from there we go. Our slope is down 4 and over 3. So there's our second point right there. Our line goes through those 2 points. Not so bad? No, good. Not all of our lines are quite that simple. We can run into one like this. What's different here? It's y plus 2. And all of our other equations have been y equals. In fact, we kind of need it that way for this to work. So down here, we need to make this just y equals. So we have to get rid of the plus 2. Well, this is just like solving any other equation that we did. We look at what's been done, and we have to figure out how to undo it. The problem is we're dealing with variables on both sides here, so it's going to be a little bit trickier. So y had 2 added to it. To get rid of it, we're going to subtract 2. So that leaves us with just y here. Now when we add or subtract, we can add or subtract one piece to each side. Now we have to do the same thing to both sides, but we only have to do it to one piece on each side. So we subtracted 2 here to get rid of that 2. We have to subtract 2 on the other side. I cannot subtract 2, though, from 3/2 x, because it has an x in it. It has a name of x. The only place we can subtract 2 is from the positive 1. What is positive 1 minus 2? Negative 1. So that becomes y equals 3/2 x minus 1. So where do I start? Negative 1. And from there I go up 3 over 2. Very good. So looking at this one, what's different here? It's 2 times y. So again, we have to get y by itself. Y has been multiplied by 2, so we need to divide by 2. We're going to divide by 2 to get rid of the 2, leaving us with just y. But when we divide or multiply an equation, we have to do it to every piece on each side. So over here, I have to divide this whole side by 2. Now the 4 divided by 2 isn't going to be difficult, but negative 3x divided by 2 looks kind of confusing. But it isn't so much. I'll show you a trick. Negative 3x divided by 2, that's just negative 3 over 2 times x. So you just put this number over that number to make a fraction and put the x behind it. 4 divided by 2 is positive 2. So what we have there is y equals negative 3/2 x plus 2. So we are going to start where on our graph? Positive 2. And from there we're going to go down 3 over 2. We might have something like this. Now here, obviously, we have more than one thing keeping y from being alone, so we're going to have to do a couple of things to it. What's the first thing we're going to have to do to try to get y by itself? Well, y has been multiplied by 3, then 1's been subtracted. Remember, when we take it apart, we take off the last piece first. So we're going to add 1. So that's gone, leaving us with 3y. When we add or subtract, we only have to do it to one piece on each side. So over here, where do I add the 1? To the 2. So this stays 2x. 2 plus 1 is going to be a positive 3. Now what do I do? Divide by 3. Leaves me with y here. But again, if I divide or multiply a side, I have to multiply or divide every piece. 2x divided by 3 is going to become 2 over 3x. 3 divided by 3 is 1. So where does that one start? 1. And from there it goes, perfect, up to over 3. Like that. We might run into something like this. Again, we want it to be y equals, so we want to get y here all by itself. Have to get rid of the 2x and the negative 3. Y has been multiplied by negative 3, and then 2x has been added to it. So to get it by itself, we're going to subtract 2x. That's gone. Leaves us with negative 3y here. What's 6 minus 2x? Trick question. It's just 6 minus 2x. Can't combine them. Then what do we need to do? Divide by negative 3. So that's gone. So we've got just y there. And again, when we multiply or divide, we have to do it to every piece on each side of the equation. So 6 divided by negative 3 is negative 2. Negative 2x divided by negative 3. Well, negative divided by negative is going to be positive. So then 2 divided by 3 is just going to be 2 over 3, or 2/3 x. So to graph that one, we're going to start at negative 2. And from there, we're going to go up to over 3. There's my second point. There's my line. So what would we do with this one? Subtract 3x. So we're left with 4y. Once again, 8 minus 3x is 8 minus 3x. And then divide by 4. Again, you have to divide every piece when you divide. 8 divided by 4, 2. Negative 3x divided by 4. It's a negative 3 over 4x. So you just have to figure out whether it's positive or negative, then you're just going to take this number over that number and make it a fraction. So now that one's going to start at what? Positive 2. And from there it's going to go down 3 over 4. Questions? Okay. So the last thing we really want to talk about is we want to talk a little bit more about this slope here. That slope can be found looking at our graphs, actually. Sometimes it's as simple as this. If I can just find 2 points on the graph that I can get the coordinates for. Like this point here would not be a good point to use because it's between markings on our graph, and it might be, what, negative 3.5 or negative 3.4 or whatever. We need to find a spot that has what we call integer coordinates, no decimals or fractions in them. Well, this point here would be a good one, and of course this one would be a good one. This one happens to hit our axes at a mark, at a hash mark. Now to get from one point to the other, I'm always going to move left to right because I want my run to be positive. So I'm always going to go running from left to right. How much do I have to rise to get up to that point? Well, I can see here I have to rise 2, right? How much do I have to run to get over there? 5. So that slope, and the abbreviation that we use for slope is the letter M, is 2 over 5. We rise 2, we run 5. We might have points like this. Again, fall right on a graph. To get from one point to the other, we're going to rise how much? 3. And we're going to run 2. You got to be careful. You got to count the spaces and not the marks. So there's 3 spaces there, 2 spaces here. So the slope is 2 over 3 or 3 over 2? 3 over 2. Rise overrun. It's not always so nice and neat on the axes like that. We can have one like this. Where we may have to count over. Find a point like this. We need to figure out how far does it rise and how far does it run. What'll rise how much here? Just 1, and it runs 4, it looks like, yes. So the slope is 1/4. We might not always have an axis involved. We might have something like this. Now the coordinate for this point is 4, 7. Yeah. 4, 7, yeah. And this one is, I'll be careful, this is a 4. The 5 is actually here. 7, 5. Good. So we have the two coordinates. From those coordinates, which coordinate, the first one or the second one, tells us the up and down here? It's the second one. It's the y coordinate. The difference is between 5 and 7 is how much? 2. So we had a rise here of 2 units, and it's actually going down, so we're going to call it a -2. We have a run. Well, the run is described by the x coordinate, the first one. What's the difference between 4 and 7? 3. So we have a slope here where we're going, since we're going down, it's a -2 over 3, or a -2/3 slope. Now there is a way we can figure this out without having to use the graph if we know 2 points. There's a formula for slope. It looks like this. What this is saying is if I have 2 points, let's say I have 7, 3, and 4, 11. Let's go 4, 12, actually. What I do, since this is y2 and y1, I pick one of them to be 0.1 and the other one to be 0.2. It really doesn't matter which one's which, so I always just go 1, 2, just like that. And what this formula is saying is to find the slope, I take the y coordinate of 0.2. So here's 0.2, its y coordinate is 12. Then I'm going to subtract the y coordinate of 0.1. So here's 0.1, the y coordinate is 3. What's 12 minus 3? 9. Then on bottom I have the x coordinate of 0.2. So here's 0.2, the x coordinate is 4. Subtract the x coordinate of 0.1. Well, here's 0.1, the x coordinate is 7. So 4 minus 7 is -3. So this is 9 over -3, which simplifies to be a -3 slope, or -3 over 1 if you want it as a fraction. Let's say I have the points -4, 1, and I am going to 6, -3. Find the slope. Well, I used to call them points 1 and 2. It's y2. What would be y2 here? -3. It's 0.2, the y coordinate, which is -3, minus y1, which is 1. Perfect. What's -3 minus 1? -4. On bottom, then it's x2, which would be 0.2. X coordinate is 6. Minus x1, which is -4. So we now have 6 minus a -4. Remember, when we subtract with negative, 6 minus a -4 becomes 6 plus a +4, which is 10. So -4 over 10, both of those can be reduced by 2 to give me -2/5. -2 over 5 is my slope. -4/10 works as well. Any questions?
Go up. I had a hard time when I screwed up on the when we found the phone.
Okay.
It's rise over run, so it's
Yep, so the rise is the difference between the y coordinates. But since this one goes down, it's a -2. Yeah. So the difference between 7 and 5 is 2, but it's going down, so we're going to make it negative.
Will that work every time we subtract those like that?
Yes, it does work every time. And if you have the picture like this, it's a lot easier. You can just take the value and you can see from the picture whether it's negative or positive. If the line's going down as you move from left to right, you know your slope better end up negative. If you don't have the picture, if you just have the points like we did down here, well, then you have to make sure you keep everything in the right order with this formula so that you can make sure it's negative or positive when you're done. A lot of times I'll just take these points and I'll sketch them out. You know, here's a graph. Here's 7, 3. Here's 4, 12. Hey, that's going to be a negative slope because that line goes down. Any other questions? Well, enough about the mechanics of dealing with the numbers of just calculating the slopes. What does the slope really mean to us? Well, the slope is actually a rate of change. For example, let's say we are graphing the amount of fluid in an IV bag compared to time. Now we said time is almost always our independent axis, the x-axis. So that would mean the amount of fluid would be on the y-axis. Now you would expect the amount of fluid to go down as the bag is infusing into the patient. It's going to get smaller and smaller. So we're going to get a line that goes something like that. So let's say that you check the chart, and on a bag that started 2 hours ago, you check the level, there's currently 800 milliliters of fluid in it. So that's actually an ordered pair of 2 hours and 800 milliliters. You come back again, let's say something's wrong with the display, you can't read the infusion rate, so you don't know what it is. You come back again at 4 hours, and the bag is now down to 400 milliliters. What is the infusion rate? Well, the infusion rate is a rate of change. How fast the level of the bag or the amount of fluid in the bag changes is the infusion rate. So if I look at this, if I make this point 1 and point 2, I'm going to just give myself some space here. Y2 is the 400, minus Y1 would be the 800. That's going to be negative 400 milliliters. Over X2 is 4 hours minus X1 is 2 hours. 4 minus 2 is 2 hours. So what this is saying is the level of fluid in the bag is negative 400 milliliters, or it went down by 400 milliliters over 2 hours. We could divide that out to get negative 200 milliliters per 1 hour. Or the bag is emptying at a rate of 200 milliliters per hour. Okay, on that note, there are a lot of pages here for homework. Page 205, 1 through 3, all. These are just kind of identifying a few things on the graph. Actually, it is 215. You're right. Okay. Actually, it might have been a typo on that sheet. It might be 205. I'm going to leave both of them up there just in case. 213 through 217, 1 through 15, the odds. 221 through 222, 1 through 15. Might have another typo on there too.
It says 1 through 155.
1 through 155. Oh, that's not too many to do.
That's pretty good.
Yeah, on page 226, 1 through 15, the odd. It sounds like a lot, but I think they'll go pretty quickly. Otherwise, we do have some time next week to go over stuff. And hopefully next week we'll have a little spare time at the end to go over the test from Unit 3 as well. You guys have a